Hi there, this is the video for section 10.6 on Karnaugh mapping. This is the first of a two-part series for this section. In section 1 we'll see what a Karnaugh map is and what the basic principles are, and in part 2 we'll look at some more advanced Karnaugh maps. Karnaugh mapping is a very clever trick for simplifying Boolean expressions and finding Boolean expressions that represent certain criteria. These were found and kind of the idea laid out by Morris Karnaugh, who's shown here, giving an explanation to somebody fairly recently in the 1950s. He found this clever way to simplify Boolean expressions. So this is another tool for our toolbox. Let's go ahead and get started. All right, first of all, we have the standard four conditions for two parameters A and B shown here. We want to create a Boolean expression that yields the results in column E. Now it's not clear what the Boolean expression is that will do that. From your experience, you might be able to look at column E and spot a relationship that would give a 1, a 1, a 1, and a 0, and that's great. We're going to use Boolean algebra to arrive at that result. And then we'll see how that would be done using a Karnaugh map. First of all, a new term. We need to recognize something called normal disjunctive form. And what normal disjunctive form is, it's the simplest way to describe the results shown on a Boolean table. So, first of all, we want to create a very simple expression that yields a 1 in row 1, a 1 in row 2, a 1 in row 3, and a 0 in row 4. Now, one thing that we'll recognize is along with A and B, we also know their negations. So we're just going to kind of acknowledge here that if A is 1100, then the negation of A parameters will be 0011. You don't have to write those down, but they're going to be useful for us to acknowledge here. And if B is 1010, then the negation of B has to be 0101. So then we can ask ourselves, okay, what are the conditions that are met to give us that 1 that we want in row 1? Well, apparently we have parameter A and B being met. So there's the first term of our normal disjunctive form. That is to say, we can have A and B. Or there's other alternatives. To get a 1 in row 2, we would need to have parameter A, but not parameter B. We want the negation of parameter B. So we would say that we could have A and the negation of B. And of course, there's a third outcome that we're hoping for here. We want a 1 in row 3. So what are the parameters or the conditions on A and B that will yield that third one? Well, apparently we don't have A, which means we do have the negation of A. And we have condition B being met. And so we would say that that third term would be the negation of A and B. And that's all there is to that. That is normal disjunctive form, and that would be our launching point. Now that we have an expression that gives these results, the question is, how can we simplify it? Well, of course, we have Boolean algebra for simplifying, so let's simplify that expression right here. Okay, if we begin with our original expression in normal disjunctive form, let's start using our Boolean properties to simplify this. First of all, we can recognize that these first two terms have a common factor of A, so we could undistribute that as such and say that that is A times B or the negation of B. We don't have to do anything with this third term just yet. But of course we know that B or the negation of B is 1, so this becomes A times 1 or the negation of A and B. Now we can simplify that a little bit more because we know that A times 1 is really just A. So this simplifies to A or the negation of A times B. Now we've simplified it quite a bit already. We started out with normal disjunctive form. We had 6 switches or 6 conditions, and we've reduced it down to 3 at this point. But we can do better than that. Let's use the distributive property of addition. That's the one that we don't use very often. We're going to distribute A using addition over the negation of A and B, and that'll give us A plus the negation of A times A plus B. Now that allows us to simplify even more because A or the negation of A, that is to say A plus A naught is 1 times A or B. And we could distribute in that 1, but 1 times anything is itself, and so we have A plus B. And there's our completely simplified expression. So yeah, if we go back and look at column E, certainly it does represent Boolean addition, A plus B. We can see that even if we get rid of our original negation column here, you can see that A or B is satisfied in row 1, row 2, and row 3, but not row 4, and that's exactly the results that we were after. Okay, I'd like you to do the same thing for this set of outcomes. This time in column E, we want to get the results 0, 1, 0, 1. So go ahead and write this in disjunctive form, and then simplify and see what you come up with. Pause the video, do that, and resume to see the solution. All right, let's start with the normal disjunctive form. Here again, we don't have to do this, but I'm going to recognize that if A gives us 1, 1, 0, 0, the negation of A will be 0, 0, 1, 1. And the negation of B will be 0, 1, 0, 1. So if we write E in normal disjunctive form, we need to have a 1 in row 2, which is satisfied when we have A and the negation of B. But we also have a 1 in row 4, which is satisfied when we have the negation of A and the negation of B. So there's our normal disjunctive form. That is a crude expression that gives us what we want in column E, but now let's see if we can simplify that. Well, we have a common factor here. That is to say we have a common factor of the negation of B. So let's pull that out, undistribute it, and that leaves us with A or not A. But you'll probably recognize that A or not A is 1, and so we have the negation of B times 1, which of course reduces to the negation of B. And there's our simplified expression for column B. And yeah, you can see that if we put the negation of B for E, we get exactly the result we want, 0, 1, 0, 1, and you may have spotted that earlier. We're done. Now, let's take a look and see what a Karnaugh map is and how it relates to this type of work. So I'm going to go back to the first problem we did in this video before I gave you the practice problem, and we're going to take a different approach. We're going to represent this table using a Karnaugh map, and then we're going to identify that simplest expression for E. Now we already know, if you remember, what our first example yielded, but let's find our result in a different way. We're going to take the same information shown in our table, but we're going to reorganize it a little bit. A Karnaugh map is based on a grid that represents all of the possible conditions shown in this table. So we're going to keep track of both the condition A and the negation of A, and we're going to do that on our top row. Now when we make the table for a Karnaugh map, we always put the negation first. And so we're going to put the negation of A and A across the top row. And then for condition B, I'm going to put the negation of B and B in the left column. Now, let's look at each one of these conditions and find out what our result is. In row 1, where we do have A and we do have B, our output is a 1. So that corresponds to this box in the bottom right. We do have A, we do have B, and that yields a 1. Row 2, we have condition A, but we don't have condition B. That is to say, this would be a case where we have the negation of B. So that corresponds to, and in that row, our output is 1. So we have A, but we don't have B, which means we must have the negation of B, which means we're in the top right box. That is to say, we have A and the negation of B and an output of 1. Row 3, we don't have condition A met, which means we must have the negation of A, but we do have condition B met. And our output there is a 1. And so the negation of A, along with condition B, that's met in the bottom left corner, and that yields a result of 1. And our bottom row here has a 0 for A and a 0 for B, which means we must be satisfying the negation of A and the negation of B, and our output is 0. And the negation of A and the negation of B is in the top left of our empty boxes, and our output is 0. So that's the same information our table contains, but we're just viewing it a little bit differently. Now here's the thing. Ones group together to tell us something about the expression. Ones that fall in adjacent boxes always have something in common. So there's two ones right next to each other here in that column. What is it that those two ones have in common? Well, they both fall in the column for A. And so we could say that those two are represented, and the thing that they have in common is column A. But we also have a couple of adjacent ones right here. Those two ones in the bottom row share in common condition B. So we could either be in our blue loop, or we could be in the black loop, which is represented by condition B. And there it is. There's your simplified Boolean expression. The ones on that table, which correspond to condition E on the Boolean table that we were given, represent the Boolean expression A or B. And of course, that's the same result we got in our first example, but we didn't have to do any Boolean algebra. Now, before we do a few more Karnaugh maps, I want to kind of summarize some important parts or important aspects about Karnaugh mapping. First of all, what should your table look like? Your tables will always look the same no matter what your parameters are doing. So anytime we have two parameters, A and B, we're going to have a table that looks like this one right here. We should have a column for the negation of A, followed by a column for condition A. We should have a row that describes every situation for B. We have a row for the negation of B and a row for condition B. All two parameter maps will build on that same table, and the columns and rows should be in that order. But what if we have three conditions, A, B, and C? Well, we still have to have a way to keep track of all the outputs. We're going to have twice as many columns, and we need to put two parameters in each column. So we'll have a column for the condition where we have the negation of A and the negation of B. But here's the thing. We want to make sure that when we make our column that we're never changing more than one parameter in adjacent columns. So we'll keep in the negation of A the same, but change B in the second column. Now our third column will keep B and change from the negation of A to just A. And in our fourth column we have A and the negation of B. So any two adjacent columns will have one parameter in common. These two have A in common. These two have the negation of A in common. These two have B in common. And if we wrap around, the last column and the first column have the negation of B in common. So you don't have to decide that. That sequence of outcomes will be the same for every Karnaugh map based on A, B, and C. And then we only need two rows to represent the two conditions on C. Again, we start with the negations. The negation of C followed by C. So whenever we make our tables, we never want to have adjacent columns or rows having more than one parameter change. And again, I'll describe that again in just a minute. Now when we group ones together, we only want to use rectangular blocks of 2, 4, or 8 when we start looping those ones together. And we want to keep them as large as possible. So let's look at a fairly large Karnaugh map and look at some ways that you can loop numbers. Okay, so this is a large Karnaugh map. This one is based on 4 parameters, A, B, C, and D. So again, you can see that between our first column and our second column, parameter A, the negation of A was kept, but we changed B from the negation of B to B. And then from our second column to our third column, we kept parameter B the same, but we changed the negation of A to just A. So there's not more than one parameter change happening. And from our third column to our fourth column, we left A the same and changed B to the negation of B. Since there's four parameters, we also have C and D, and we follow the same idea down the left side. We start out with the negation of C and the negation of D, and then we'll leave C the same but change D for row 2, and then we'll leave D the same but change C for row 3, and we leave C the same and change D in row 4. And if we were to wrap back around, we would leave the negation of D and change C back. And so even wrapping around, not more than one parameter is changing. Now look at all those ones. We want to group them together, but we can only do it using squares and rectangles and only boxes of 2, 4, or 8. So look at that and see if you can find large groups of 1. Well, first of all, we have a pretty big group of 1s right here. That's a 2 by 2 box. That's a good grouping. Now it's okay to overlap, and in fact overlap is usually a good thing. Now below that we have a couple of 1s, and it's tempting to want to just group those two together, but that's not as big as possible. Even though there's overlap, it's better to go up and get those 2 1s above it as well. And so there's a large group of 4 instead of that small group of 2. Now that leaves us with a couple of lonely 1s here. It's tempting to go up here and grab this 1 and just box it in by itself, but it could be bigger than that. We can go over and grab this 1 right next to it. Now we can't go any further than that though, because that would make a group of 3. So we'll have to stop there, and we can loop those two together. That's a good boxing. And our last one, which is over here, it seems like that one would have to be by itself, but we can always wrap around the edges on a K-map as well. So we can box on this 1, and we can actually wrap that over and come over here and grab a 1 right next to it. Now it would be nice if we could come over and grab this 1 here, but we can't, because that would make a group of 3, and we can only group 2, 4, or 8, or if possible 16, but that's unlikely, together. So the 4 groups that we have shown here are all good groupings. And these groupings all have a common parameter as long as we follow those guidelines. Now I want to show you a couple of errors. Here's another fairly large K-map, and I want to show you some common mistakes that I see when people group. None of the types of groupings here I'm going to show you are acceptable. Sometimes I see people group together in that way. Do you see what's wrong with that? It's a group of 6. We can't do that. That's no good. Sometimes I see people group in irregular shapes, like this. That's not allowed either. That's a group of 3, and it's not a rectangle or a square, and so no L or funny shaped groupings. So it would be good if we grouped those 4 1s together. And it's tempting to take these 4 1s and put them together. But do you see why that's not a good grouping? That's an allowed shape, but there's also some 1s over on the right side under A negation B that we should group with that. So instead of grouping those together, we should group all 4 of these together and wrap it around with the 4 that are over here. And that gives us a nice big group of 8, which is even better. The bigger the groups, the simpler our Boolean expression will be. So we'll keep that grouping. And in addition to that, we'll go back and keep the original group that we had there. Tempting to wrap that around, but that would make a group of 6. Now that leaves us with a lonely old 1. And again, it seems like we maybe just want to box that one up on its own, but we shouldn't do that. We should group it with at least one adjacent 1 and more if possible. So we could group these 2 1s together, and that would make a group of 2. Or we can go up and group those together, and even though there's some more overlap, that's a group of 4, and that's better yet. And so that would be the best looping scheme to include all the ones that were shown here. Okay, based on what we've just done, I want you to take a minute and represent this Boolean table on a Karnaugh map, do your grouping and see if you can identify the simplest expression for E. Pause the video and resume when you're ready to see the solution. Okay, let's take a look. We don't need the box in the top left. Since this is only a two-parameter Boolean expression, we just need to make a Karnaugh table for A and B. So we'll list the negation of A and A across the top, and the negation of B and B along the left side. That'll be true no matter what our outcomes are. So first of all, let's take a look at row 1. Row 1, we have conditions A and B. That means that we're looking at the box in the bottom left right down here. The outcome there is a 0. Row 2, we have condition A but not condition B. So in other words, this will correspond to A but not B, the box right above it. And in that box we'll have an outcome of 1. Row 3, we don't have condition A, which means we do have its negation, but we do have B. So the negation of A and B, that's going to be represented by this box in the bottom left. Our outcome there is a 0. And in row 4, we have neither A nor B, so that's the negation of A and the negation of B. That is our top left box, and our outcome there is 1. Okay, now that we've filled in our table, we can do our looping. There's only 2 ones there, and so that makes the looping real easy. One box covers both of our ones. Now, what does that one box have in common? That one box has in common the parameter negation B. And so that means that column E is represented by the negation of B, which of course makes sense. Column B was 1, 0, 1, 0. The negation of B will be 0, 1, 0, 1. That's the same thing you got when you simplified that using Boolean algebra a minute ago. Okay, well now it's time to start looking at some more complex maps. So that's the end of part 1. You can go ahead and watch part 2, where we'll pick up right there and look at some 3 and 4 parameter maps.